The fine art of fire, commonly referred to as fire assay, is the best method used for the collection and the refinement of the precious and noble metals when it is practiced by the small-scale miner or prospector. It is the lesser expensive method of the collection and refinement. If your concentrations are high enough, this method will collect all of the gold, the silver, and the platinum group metals in your concentrates or sample material. The first step of the collection uses the methodology of collection and separation prior to refinement. The first step in the process, as you should be well aware of now, is taking your concentrates, mixing them with the required flux, and melting the charge, thereby producing two molten solutions of different densities of which the separation of the two alloys, when cooled, can be accomplished. In this presentation, I will be discussing the creation of the lead buttons. Welcome back. I'm Rob Boyko, Boyko Mineral Exploration. In presentation 6, I discussed the characteristics of the Class 1 ores. Class 1 ores are neutral, and therefore will not react chemically with another molecule. These ores are not reducing or oxidizing. I also showed you how carbon will reduce 2 molecules of litharge, that is lead oxide, to 2 atoms of elemental lead, which is required for the collection of the gold and silver, etc. Flour that is unbleached, natural, and not fortified is a lot cheaper than charcoal and is the most commonly used reagent. This reducing agent has a reducing power of 11. In other words, 1.25 grams of flour will reduce enough lead oxide to form 11 grams of metallic lead. A 28 gram to 30 gram button is usually aimed for, as this size of button produces a much better cupellation, a subject in an upcoming presentation. You know that silica melts at 1750 degrees centigrade. Lead oxide melts at 883 degrees centigrade. This lowers the melting temperature of the silica, and the two will start to alloy together as a slag. Lead oxide is required to fuse with the slag as well as produce a lead button of a suitable size. The question arises, how much lead oxide is required? I have suggested that one downloads a copy of the periodic table, as we use the molar or atomic weights of each element in the periodic table to calculate the flux requirements. As shown in the slide, using the periodic table, for reference, elemental lead is shown to be 207.2 grams, and oxygen is 16.0 grams. Adding them up gives lead oxide an atomic weight of 223.2 grams. The amount of lead oxide required is simply calculated by dividing the atomic weight of the lead oxide by the atomic weight of the elemental lead, and then multiplying the amount of the lead button in grams that is required. As shown, the amount of litharge required to produce a 28 gram lead button is 30 grams. 2 grams of lead oxide is used for the fusion of the slag. Class 2 ores are reducing, and in most cases have high reducing powers. Others may have a low reducing power. For those that have high reducing powers, in order to maintain a 28 gram lead button, niter, which is the common name for potassium nitrate, is used to inhibit the formation of an excessively large lead button. Niter is an oxidizing reagent, which is used to oxidize the lead back into lead oxide. This slide may be a little confusing at first. The example here is the reaction with pyrite. When heated and everything in its own order decomposes, there will be different products forming. As shown, the 5 molecules of pyrite react with 14 molecules of niter. This is a balanced equation, and the products are shown. At the same time, however, the pyrite also reacts with the litharge, and the litharge is reduced to 7 atoms of lead. What this means is that the 5 molecules of pyrite will reduce 7 molecules of litharge to 35 atoms of elemental lead. Taking the same perspective in terms of molecular weight, the 5 molecules of pyrite have a mole weight of 598.5 grams. This means that the pyrite has reduced the litharge to 7,252.0 molar grams of elemental lead. Now keep in mind that the molecular weight of the 14 molecules of niter is 1,415.5 grams. It can be said that the niter will oxidize the molecular weight of 7,252 grams of elemental lead. The result will be that 1 gram of niter will oxidize 5.12 grams of elemental lead. It will then be considered as having an oxidizing power of 5.12. However, there will be some loss in the oxidizing power of niter. During fusion, dipotassium oxide, along with nitrogen gas and oxygen being expunged, the oxidizing power is reduced by 20%. The oxidizing power of niter is actually 4.0. This is a magic number to remember. The reducing of power of flour is also a magic number to remember. A reducing ore or sample may have a high oxidating power, which in turn produces a button that is way too large. For example, if the button produced was, let's say, 50 grams, 50 grams would be too large for cupellation and parting. A 28-gram button is what most will aim for. That would mean that 22 grams of lead would have to be inhibited from being produced. This would require that 22 grams of lead would have to be oxidized back into lead oxide. Since niter has an oxidizing power of 4, dividing the required amount of lead to be inhibited by the oxidating power will give the amount of niter required, which would be 5.5 grams. In many of the textbooks you will find calculations as the one shown on the left. Others are hard to follow and some are extremely confusing. So let's get practical. This example of calculating the required amount of niter required is quite simple in practice. This example is an ore consisting of 70% zinc sulfide and 30% quartz. Since the quartz is a class 1 component, there will be no chemical reaction and therefore not in the equation. Also, you will notice that a portion of the flux used contains soda ash, being sodium carbonate. I will also assume that you may not know the workings of the assay ton system and therefore added the calculation in the slide. There are 7 easy steps. The most challenging may be the writing of the balanced chemical equation, which is required for the calculations. In the first step, 0.5 of an assay ton is weighed out. The magic number here to remember is 29.166. Anywhere between 0.25 to 1.0 assay ton may be used. 0.5 is the normal amount. More on this later. Second is the balanced equation itself. All these constituents will break down into oxides and gases. The starting point is to write down what your sample constituents are on the left side, and on the right, the product constituents. I want you to take notice on the right side, there are 7 oxygen atoms. On the left, you will need 4 molecules of litharge to balance the 7 oxygen atoms. That will also increase the number of lead atoms on the right. In step 3, it's quite easy to calculate. Since the quantity of sphalerite in the 15-gram sample is only 70%, that will equate to 10.5 grams. Step 4 is also simply using the periodic table, calculating the molar weights of the elemental lead and the molecular weight of the zinc sulfide as shown. Step 5 is the calculation of the reducing power value itself. It is a simple division process. The number of moles times the molar weight of the lead divided by the number of moles times the molecular weight of the zinc sulfide yields the reducing power of the ore. Since, as shown, we have 4 moles of the lead times the 207.2 grams, being the molar weight, divided by the 1 mole times the molar weight of the zinc sulfide, which is 97.5 grams, the resulting reducing power is 8.5, meaning 1 gram of ore will result or produce 8.5 grams of lead. Since we have 10.5 grams of sphalerite, times the reducing power of the 8.5 will give us a final button size of 89.25 grams of lead. Now, wanting a 28 gram button, the excess lead of 61.25 grams must be inhibited. Since the oxidizing power of the niter is 4, the 61.25 divided by the 4 gives us the amount of niter that needs to be used to inhibit the excess amount of lead being formed. In this example, it's 15.3 grams. In the last or previous slide, that is, for the reaction equation, I added soda ash. Sodium carbonate is used in every crucible fusion. It reduces fusion temperature, eliminates carbon in the form of carbon dioxide gas, and more. But the most important is that it combines to form the silicate slag. Let's turn the table around a bit. In this example, we still use the sphalerite ore. However, the zinc sulfide constituent has been reduced to 10%, leaving 90% as quartz. Step 1 through step 6 is the same, and so are the rest of the calculations. The difference here is that the sphalerite concentration is only 1.5 grams. The reducing power of the ore is still 8.5. This results in a lower yield of metallic lead being only 12.7 grams. Since the required button size is 28 grams, the yield is 15.2 grams short. In a previous slide, I discussed the reducing power of flour. The magic number to remember was 11. 11 is the reducing power of flour. Since 1 gram of flour will reduce lead oxide to 11 grams of lead, by dividing the 15.25 grams of additional lead required by the reducing power of the flour, the result is 3.8 grams of flour to be added to the charge, which is needed to produce the 28 gram button, not the niter. The calculations regarding the oxidating power of the class 3 ores are basically the same as those of the reducing ores, but there is a small difference. The sample on the left is tantalite, which is an oxidizing ore. The ore type for this example is magnetite. Because the lead oxide is inhibited during fusion from being reduced to elemental lead, the amount of lead that needs to be compensated for must be taken into account. In step 7, notice that the calculation is not a subtraction, as we did for the lead calculation regarding the reducing ores. In this instance, we are adding the amount prevented to the amount required. Using the magnetite as an example in step 7, the grams of lead that was prevented was added to the 28 grams required for the lead button, giving a total of 41.425 grams to be compensated. The flour, which is reducing agent, having an RP of 11, resulted in the amount of flour of 3.8 grams to be added to the charge. Also note the equation in step 3. Since the ore is oxidating, the lead oxide will not decompose or reduce. The chemical reaction is such that any addition of lead will result in additional lead oxide. Therefore, we can make a theoretical assumption that the elemental lead is being introduced. Hence, the reaction side of the equation is showing lead as a reagent instead of lead oxide, as would be for other types of ores. Even though lead is not being added as elemental lead, this would be the amount that would be compensated. The lead oxide would have to be reduced, and therefore flour is added. In this presentation, I discussed the oxidizing and reducing powers of the three classes of ores. I went over the calculations used to determine the amount of niter or flour that would be required or added to the charge as a flux to produce a lead button of the preferred 28 grams. I also discussed the amount of lead oxide it would take for a neutral ore in regards to the slag formation, along with the calculation. It had been said that one does not need the lead oxide to perform a crucible fusion, and that would be correct. However, the result would be losses of precious metals in the slag. There is an alternative, but this is used for the determination of low-grade platinum group metals. It is the nickel sulfide method. This method is used, or usually used, that is, conducted in a laboratory, where instrumental analysis is used for the final results. As for the lead oxide, it is still the best collector for the precious and noble metals, and should not be discarded for other alternatives. Without the lead oxide, or lead when scorification is performed, your result would be low. In the next presentation, I will be discussing some of the special treatments for those sulfide ores, as well as a couple of do's and don'ts. I would like to say thank you for watching. As always, if you are viewing this as the recorded video presentation, the channel that I post these presentations on are not commercialized. My only reward is a like if you find it interesting and helpful, and a share if you know someone out there that may benefit from this information. I'm Rob Boyko, Boyko Mineral Exploration.